Welcome back. We're going to start with the next section of chapter 1, which talks about power series, analytic functions, and the extension theorem. So the first and maybe most important idea of complex analysis is that the way that we set up the definition of differentiability was very careful, right? So we want to stay away from the idea of functions that are differentiable just at a point. And instead, remember that for us, differentiable means that we're differentiable on some open disk around some point. So when we say differentiable, we mean that a function has a local linear approximation on some open set. And that turns out to be a structural assumption that clarifies a lot of the difficulties with real analysis. So the big theme of basically all of complex analysis is that differentiable once means infinitely differentiable. In the sort of language that we're going to introduce in this chapter, it's the relationship between a function being holomorphic, which if you recall was differentiable on an open set, and a function being analytic, which as we'll see is possessing a convergent power series on some open set. So this theme is going to carry through the rest of the course. The idea here that we can pivot back and forth between a function possessing a convergent power series in an open set and a function having just a single derivative. And that, that really structures the sorts of functions that we even have that we're going to work with in complex analysis. So I'm going to point out that the theme that we've identified here is completely untrue for real value functions. Once differentiable on an open set does not in any way imply anything about further derivatives for real value functions. Real value functions are terrible. And in fact, in the study of real analysis, part of what you're doing in a real analysis sequence at the undergraduate and graduate levels is dealing with the fact that real value functions are pretty badly behaved and coming up with sets of conditions that you can use to check when you can actually do interesting calculus with them. So the worst function that I know is the Weierstrass function, w of x. And so w of x is a function that is defined in such a way so that wx is continuous everywhere and differentiable nowhere. And you can use the Weierstrass function. This is the worst kind of function that you can cook up. Pretty awful. And you can use because it's continuous, you can integrate it. So you can use the fundamental theorem of calculus on it. So if you use the fundamental theorem of calculus on this thing, you can define a function w of x, which is the integral from any base point you want, say the integral from 0 to x of little w of t dt. This is a perfectly well-defined function because the fundamental theorem of calculus applies to continuous functions. Now, by the fundamental theorem of calculus, the derivative of w of x is little w of x. This is by the fundamental theorem of calculus. So capital W of x is a function, the integral of the Weierstrass function is a function with one derivative, and it's differentiable everywhere. And the second derivative is differentiable nowhere. So it is not the case for functions of real variables that we get any information from a single variable existing, not even from a point-to-point location. So complex analysis is unique in that it eliminates these sorts of examples. And it's actually part of the reason why complex analysis is ubiquitous in applications, is that the natural functions that you want to use when you're studying systems in the physical world are functions where you don't have this kind of behavior. Okay. So now we're going to move on to defining our second set of important functions, which turn out to be equivalent. First, I'm going to forcibly remind you here that when I say holomorphic, I mean differentiable once on a disk of positive radius. Okay, so an open disk. So an analytic function, just like in real variables, is a function that has a convergent power series. And for us, we want that convergent power series not to allow the possibility that the radius of convergence is 0. So when I define an analytic function, I have a complex function that has a convergent power series on some set where that radius is not 0. So analytic functions are functions with convergent power series. Now, if you recall from real calculus, functions having power series are pretty nice functions. And in particular, one of the nicest things about analytic functions is that analytic functions have infinite derivatives. So to be represented with a convergent power series is essentially saying that you're the limit of polynomials, or that you are infinitely differentiable. So very smooth functions. Analytic functions can't have nastiness in any derivative. And like I said, the central result of complex analysis is that f being holomorphic is equivalent to f being analytic. That is, possessing one derivative for a complex function is enough to imply, right, again, on an open set, possessing one derivative on an open set is enough to imply that you're infinitely differentiable in an open set, which is a striking difference from the real case. Now, we can prove one of these directions right now. It's not hard to believe that if a function has an analytic, or if a function is analytic so that it has a convergent power series, then I should be able to differentiate the power series. That has to be proved, but that's still true. The direction, in fact, the only complication there is that we need to show that when we take the derivative of the power series in a formal way, that the object that we get out the other side is actually convergent. The other direction is trickier. So that's the direction where holomorphic implies analytic. That is, once differentiable implies infinitely differentiable. And it's hard to see why that would be the harder direction. And to do that, we're going to need Taylor's theorem. So that is the Taylor expansion, so that we have a way of generating the coefficients of a power series, and when we know such a series exists. To do that in complex analysis, we're going to need a beefier set of tools. We're not going to be able to do that right now. So that's going to be held off in the Johnston text that shows up in chapter 2, I believe, after you get the Cauchy integral formula, and that's where we'll see it. So for now, we're going to build from the bottom. We're going to study analytic functions. We're going to prove that to be analytic is to be holomorphic. We're going to leave off the reverse implication for now that holomorphic implies analytic. And so we'll pick that back up. That sort of like completes the circle of the basis of complex analysis. So I'm going to give you an idea of how the proof of, maybe not the proof, but the tools behind the proof, because these are important tools that show up even in sort of applications and computing examples. And then I'm actually going to walk you through proofs of these theorems, which, of course, for those of you that are interested in applications are not necessary, but it shows you how complex analysis leverages the tools of real analysis to just by extension, basically. And in fact, in this chapter, we're going to get the extension theorem, which lets us formally view complex analysis as basically just putting z's in place of x's in real calculus. Okay, so for an outline of the proof that a function is analytic implies that a function is holomorphic, we need a set of tools that we can use to analyze power series and the convergence of power series. And some of the most important tools that we have available to do that from real calculus are the Weierstrass Mtest, which is a way of saying when a function converges. When the power series of a function converges, it's a way of relating the coefficients of a power series to absolute convergence of regular series of numbers. The root test, which is a way of investigating, it's the standard tool for investigating the coefficients of a power series and determining what the largest radius of convergence of a power series is. And then finally, what's called the infinitely differentiable theorem, which is the argument that lets us show that a power series can be taken. You can take the derivative of a power series just like taking the derivative of a polynomial, and that the series that you get out the other side is actually convergent. Okay, so that is basically all of these pieces together are going to be used to construct the theorem that once differentiable, sorry, wrong different direction here, that convergent power series if you have, say, f of x is equal to the sum of z from n to infinity of some coefficients. You see here to keep in correspondence with the book, z minus a to the n, that if this converges on a disk, say S, of radius r greater than 0, then formally f prime of z, which is the sum from n equals 1 to infinity of n c sub n z minus a to the n minus 1, also converges on the same disk. And in fact, since it is a convergent power series, it will have a derivative. So you can continue this process forever. So if you're analytic, you are once differentiable, which implies that you're infinitely differentiable. Okay. So now is going to begin the sort of theoretical discussion. So those of you that want to move forward in the video, you're welcome to do so. So we're going to begin by talking about the Weierstrass Mtest. And I want to kind of give you an idea of what's going on with the Mtest first. This is a standard result in analysis and a very important one for understanding how a power series behaves. So the Weierstrass Mtest is a way of saying when a series of functions adds up into a meaningful object at the end. So in particular, the way you should think about the Mtest is it's a way of relating the coefficients of a power series to the convergence of the power series. So the main idea is that if you have the terms of a power series, each bounded by some mn, so that is the first term is less than or equal to mn inside of some disk. The second term is bounded by m2 and so on. I guess I can make this more clear. What we're saying here is that C1 z minus a to the first is less than or equal to m1, and C2 z minus a squared is less than or equal to m2 for all n and for all z's on the disk. So this is, so we could keep this going for all n and n, which means every term has a bound. And for all z inside this disk, so that z minus a is less than r, right? So the idea here is each individual term is bounded by some number. And then if the numbers, if those bounds themselves add up as a series, then the original power series converged uniformly and absolutely on that disk. So the Mtest says that if the terms are individually bounded, if every term is individually bounded for all z's inside of some set, and if that series of bounds adds up, so now we just can use regular old convergence of numbers here, then the original power series converged uniformly and absolutely as a series of functions on the disk. So the very powerful result. The basic proof of this result is the following. So if m is greater than n, without loss of generality, assume we have the series extended out to the mth and nth terms. We're going to look at the mth and nth partial sums. Then we'll let the partial sums be smz minus snz, which is the sum from n equals n plus 1 to m. Remember, m is further out in the series than n was, of say cn z minus a to the n. And that's, of course, going to be less than or equal to mn by assumption. So let's look at, so by assumption, since these are all individually bounded, this is saying that this is less than or equal to the sum from n equals n plus 1 to m of mn. But since by assumption this was bounded, then this object, so the tail of this sequence of sort of subtracted partial sums, and this must tend to 0 as m and n go to infinity. And that means that the sequence of partial sums Sn, this is an argument to show that this is a Cauchy sequence. So basically, the hypotheses of the Weierstrass Mtest allow us to conclude that the sequence of partial sums for our original series is a Cauchy sequence. And it's a Cauchy sequence that's bounded for all values of z inside the disk, which is, exactly what we mean by a uniform bound or uniformly convergent. And so Cauchy sequences converge. The Cauchy sequences here converge for all values of z in the disk. And so we say that Sn converges uniformly on the set z minus a is less than r. That's basically the end of the argument. The same argument shows absolute convergence. Okay. All right. Now, even from a computational standpoint, the next theorem here is very important when you're working with power series, and in fact is the standard tool for analyzing what the radius of convergence of a power series is. So the root test is a way of looking at a power series and computing a number called the radius of convergence directly from this limit. And what the root test tells you is where the function, it's going to give you a number that indicates what from the center, this sort of a value right here. So this center that you've started looking at, what is the largest disk on which your power series centered at that number a is going to converge? So you can imagine when you're finished, you're going to have some value a, and then the distance r here is going to be a way of measuring what the largest disk is on which your original power series converges. And it's better than that, actually. So not only is it the largest such r, but it also tells you expressly that like on the outside of the disk, the function is actually divergent. Now it's possible here that r can be infinity, in which case the function is called an entire function. It's power series everywhere. Okay. So what the root test says is that if you start with a formal power series, and by formal we just mean a pile of symbols that we do not yet know whether or not it converges. I can always write that structure down without knowing if it actually defines a function. So in order for a power series to define a function, it must actually converge uniformly and absolutely. And that's what the root test is going to tell you. So we suppose that we start with some formal power series, and then we compute this limit where we take 1 over the square root of the absolute value of the terms. Remember, these could be complex numbers. There's an error here because these are supposed to be CNs. So this is supposed to be CN right here. These are not some new quantity here. You take the coefficients of the power series, you plug it into this calculation, and then whatever that R value turns out to be, the series is going to converge absolutely in this disk. In fact, we can actually just draw a picture real quick here, maybe a better picture, because there's little r's here as well. So the idea is you have some a value, you have a disk around it. The radius of this disk is r. On the interior of that disk, you converge absolutely. So this is absolute convergence in here. On any smaller disk, so say the radius of this is r, this is uniform convergence. And now here you have divergence. So the root test completely characterizes the behavior of the power series. So we should say r is called the radius of convergence. Because this theorem is a result from calculus, we're going to leave it here because essentially the same argument that works in calculus works here with the replacement of absolute value with the modulus of a complex number. So it's the same argument, a standard result in a undergraduate real analysis course. And not terribly enlightening. The proof does use the Mtest, which is why you need the Mtest. So the proof of this basically goes by applying the Mtest. And certain estimates involving the R that you computed using this formula right here. Okay, it's just not very enlightening. So I'm going to leave this proof aside and refer you to many of the excellent undergraduate texts in real analysis. For example, you could see the proof in Abbott's Understanding Analysis. Or if you want something, a higher level version of this, you can go look in, say, Axler's Measure and Integration. All right, so now we've arrived at the sort of big theorem for the section, which is called the infinitely differentiable theorem. And it's the seemingly obvious assertion that if you have a power series with a radius of convergence here, that such a function actually turns out to be differentiable as well. But you should think for a second about exactly what that means, right? That for a function to have a power series is differentiable, which is maybe an assertion that you took for granted when you saw it in calculus or in real analysis, certainly in calculus. The way that this is typically thought of is, well, you just take the derivative of the power series like it was a polynomial. The problem is that in order for that to actually work, you need to know that the derivative defined in terms of the difference quotient, which is this f prime of z, remember that's given in terms of a difference quotient that looks like the limit as h goes to 0 of f of z plus h minus f of z over h needs to somehow be equal to this convergent power series, the sum from n equals 1 to infinity of n cn z minus a to the n minus 1. And so there's more going on here than just taking the derivative formally of the power series and then saying it's the same thing. You need it to actually be convergent. This, in order for this to be a meaningful statement, this limit and this convergent power series have to be the same object. And that's actually, this is sort of a difficult proof precisely because this is kind of a complicated set of ideas. But again, here we have a limit of a difference quotient. And here we have a hopefully convergent power series. And it's not enough just that the series is convergent. It has to converge to the same function that's illustrated or that's given by this this difference quotient over here. I've got sunblock in my eye. Okay, so the proof of this and the proof of the previous theorem I'm going to put into a supplemental video. This is a long argument. It's mostly an estimate. And the idea is, the way that it works is it takes an equation that looks like this. So the idea of the proof here is what I'll indicate. The idea is that you look at this difference quotient, f of z plus h minus f of z over h, and you subtract off this power series that's supposed to represent the derivative, n c to the n, z minus a to the n. And the idea is to show that that difference gets small as h goes to 0. So to show that the difference gets small as h goes to 0. And it's quite a technical argument. So I don't want to spend time in this video doing this proof. I do think the proof is important if you're interested in looking at how some of the analysis running around in the background works. There's some estimates in there that are important. The idea is essentially to turn it into one power series and then apply the root test to it. So how? Turn the difference into a power series, and then apply the root test. Like I said, I'll put it in the supplemental video, but I don't want to burn too much time on essentially a 20-minute argument. Okay, so what do we have now for our complex analysis so far, right? So we've got the idea of analytic. So this is sort of where we are. So we know that analytic means it has a convergent power series. And our first big theorem is that this implies infinitely differentiable in the obvious way. But where are we going to get power series? Where are they going to come from? That's sort of a big question we should have, is where are we going to get power series? Where are we going to get a library of functions we can even get out the gate with? After all, we don't know Taylor's theorem yet. Taylor's theorem is not going to show up until much later when we have the Cauchy integral formula. So we need a really big tool to prove Taylor series. And the answer turns out to be a theorem called the extension theorem. And this particular approach to complex analysis is so useful and so intuitive, because what the extension theorem is going to tell us is that complex analysis really is just an extension of calculus. That the functions of calculus and the theorems of calculus that were true for analytic functions there turn out to still hold for complex functions, basically just by putting z in place of x. So basically, if you combine the root test, which involved absolute value, which can be replaced with modulus of complex number, and the Mtest, which is defined in terms of the absolute value and can be replaced. But remember there that the Mtest was purely a bound on the size of the terms of the series. That's perfectly okay with complex modulus in place of absolute value instead. And what that means is that a real power series with a positive radius of convergence will still be convergent if we think about it as taking complex entries instead. So this is our first big theorem here, our second big theorem. It's called the extension theorem, and it gives us a body of functions that we can work with. This is a very important theorem because it says any real valued analytic function with a convergent power series with either a positive or infinite radius of convergence R can be extended to a complex analytic function f of z by replacing x with z with the same radius of convergence. Okay. It's a striking theorem, actually. And the proof of this one's pretty easy, because the proof of this one just says, well, okay, so without loss of generality, let's let a be equal to 0. And let's just suppose that we have an f of x is equal to the sum from n equals 0 to infinity of cn x to the n, and suppose that it has radius of convergence r. Or if you like, it converges on the real, say, the real interval from minus r to r. So the interval of convergence, there's an idea from calculus 1. Well, the root test then, if this is the radius of convergence of this thing, the root test is going to produce the same number, right? So the root test with complex entries is still going to give r is equal to the limit as n goes to infinity of 1 over c to the n to the 1 over n with no difference. It's same radius of convergence. You should think about it like this. You have minus r, you have r, you have this interval where the series converged originally, but the root test says that everything's actually okay for complex z values as well, which means really these things sit inside some disk. So the function was real analytic here. But the same root test with the same coefficients is going to say that that same power series converges on the whole disk of that radius. So it's complex analytic on the disk that has that original real interval as its diameter in the real axis. That's essentially the proof. I mean, the Mtest and the root test apply to complex series, and we inherit the radius of convergence and the coefficients from the real series, and we just plug them into complex series. So that's basically how extension works. We inherit some coefficients and a radius of convergence from the sum of Cn x to the n, but the same exact radius of convergence and coefficients are going to work with the same exact theorems for complex entries as well. Use the root test, the Mtest, get the sum of Cn z to the n. It's just literally a straight replacement. And the beautiful thing about this is we don't just get the fact that anything we write down as a power series extends. We actually get more. We get that any identities involving real analytic functions carry forward as well, which is pretty awesome and incredibly useful. So, for example, you get stuff like this. Things to do with the extension theorem. Well, any power series you can write down that's real analytic with an interval of convergence automatically turns into a complex analytic series as well. So, here's an example. Like, just start writing down your favorite functions. F of x is equal to u bx. Well, that has a power series. We know the real Taylor formula holds. N is equal to 0 to infinity of x to the n over n factorial. Oh, and the radius of convergence here was infinity. Well, it turns out that the complex version of this, you just say, oh, that means f of z is equal to e to the z, which is the sum from n equals 0 to infinity of z to the n over n factorial. Has the same radius of convergence and defines a perfectly good complex analytic function. We get, say, this. So we have f of x is equal to cosine of x, which is the sum from n equals 0 to infinity of -1 to the n over 2n factorial x to the 2n, and the radius of convergence is infinity. And f of x is equal to the sine of x, which is the sum from n equals 0 to infinity of -1 to the n over 2n plus 1 to the n, factorial. Get out of here. X to the 2n plus 1 with r is equal to infinity. You just plug in z. F of z is equal to cosine z, which is the sum from n equals 0 to infinity of -1 to the n over 2n factorial x to the 2n, and f of z is equal to the sine of z, which is the sum from n equals 0 to infinity of -1 to the n, 2n plus 1 factorial x to the 2n plus 1. And even better, identities involving sines and cosines, well, those involve functions that have convergent power series, right? You can mix functions that are analytic together and they stay analytic as long, you can sum power series together as long as everything is absolutely uniformly convergent, which means any relationships between these functions continue to hold as well. So the extension theorem also implies things like this. Because cosine squared of x plus sine squared of x is equal to 1, well, cosine is analytic, so cosine squared is analytic. Sine is analytic, so sine squared is analytic. 1 is an analytic function. This is a relationship between analytic functions. This tells you that cosine squared of z plus sine squared of z is equal to 1, continues to hold as well. So identities also hold. Identities extend. And in fact, we can say even more about identities extending, but this is sort of like the big deal with what the extension theorem does, is it lets us carry forward a lot of the ideas of calculus and real variables and push them forward into complex analysis. So the thing we're missing here. So the thing we're missing is, how do we come up with power series for functions where we don't have a real analog? What if I have a function that's defined in complex analysis that doesn't come from a real analytic function? Or do we have a natural way of developing a complex power series in the absence of a real analytic formula? And the answer is, this is to get more than that, to go beyond the extension theorem, we're going to need the Taylor series. Okay, so the final thing I want to talk about today is what's called the identity theorem. And what the identity theorem says is that complex analytic functions, there's not very many of them. And they turn out to be a much smaller family of functions than the usual families we deal with in real analysis. And there's a reason for that. So the first is, we're asking these functions to be infinitely differentiable, right? We're going to work with analytic functions. Analytic functions have to have convergent power series, which mean they have to be infinitely differentiable, which means they have to be very smooth. So we're working with a really cut down family of functions. But it turns out to be the case that complex analytic functions have this perhaps not all that unsurprising behavior that if they agree on some overlap, then they're actually the same function. So what do I mean by that? Suppose you have f, and say f is defined on some disk S. So f is analytic, which means that it has a power series on some open disk. And suppose that we also have some function g, which is analytic, and it has a power series defined on some other open disk. So say, over here, g is equal to dn z minus b to the n. And here, f is the sum of cn z minus a to the n. So here's a, and here is b. It turns out to be the case that if these functions agree, if they're identical to each other on this overlap, so if these functions agree on an overlap for all values in the overlap, so that's what we mean here. If f is equal to g on some non-empty open disk S contained in the set U, where f and g are both analytic. So you have to imagine that there's some big set U here. The S referred to in the theorem, it lives inside this overlap. So what we're saying is if there's some place in the middle here, so there's some disk S where f and g are identical to each other on the little disk, then there's the same function everywhere on U. If f is equal to g on this little disk S, then f is equal to g on all of U. Okay, so agreement on an open set forces the functions to be equal everywhere. And that's another big difference with the real case, because you can imagine having very nice real functions that have a case that maybe they agree with each other, not at a point, but like on some interval somewhere. And then they deviate, like piecewise functions, or functions that are, it's possible to define functions, say, that are 0 someplace and then hook into some kind of exponential function, and where they meet, they're perfectly smooth, right? Infinitely differentiable. What this is saying is that it's not possible for functions to agree on some set, like maybe they're both equal to 0 for a while, and then one of them goes up and one of them goes down. What I mean here is picture something like this. You can imagine in the real case that you have maybe a function that hits a bend and goes up like e to the x, and you can make this thing infinitely differentiable. It's pretty easy to do. Or you have a different function that when it gets there, it turns and goes down. So that is, the two functions agree with each other on this interval, and then one goes up and one goes down once you get past it. That can't happen in the complex analytic case. In the complex analytic case, agreement on any open set where they're contained in a domain where both functions are analytic forces the functions to be identical everywhere on their domains where they're both analytic. It's an enormously useful idea. And it, again, what it's supposed to indicate to you is how few complex analytic functions there are in comparison with the functions of calculus, which are continuous functions, and of course can agree on any number of sets and not be the same function. Okay, so the upshot here is what we've covered in this sort of lengthy lesson, but one that is a sort of underpinning for where we go with complex analysis, is we defined the notion of what it meant to be analytic, which meant convergent power series. We established, though did not prove, the infinitely differentiable theorem, which says that an analytic function is infinitely differentiable. We proved the extension theorem, which says that real analytic implies complex analytic. And we talked about the identity theorem, which says that f is equal to g on some small s implies f is equal to g on a big U where f and g are analytic. And so these are sort of the basic fundamental theorems that underlie everything that we're going to do from here. And again, sort of our white whale, if you will, if we're going to put this in terms of Moby Dick, is what we're chasing here is the reverse implication, which is the idea that once differentiable, that is holomorphic, also implies analytic. All right, so take this in small bites, read the book carefully, and I'll have a supplemental video posted with the proofs. All right, until you guys next time.